The first substitution reaction we're going to explore is called the SN2 reaction. Now, I've already mentioned that primary alkyl halides and some secondary alkyl halides will undergo SN2 reactions. This is where a nucleophile reacts with some substrate that has a leaving group, and the leaving group is typically halide, but we're going to see there are other leaving groups. And what happens is the nucleophile displaces the leaving group, so you get a new a substrate with a new functional group on it, and the leaving group comes off typically as a negatively charged anion. So in an SN2 reaction, we know that the rate is dependent on the concentration of the alkyl halide, so RLG, and it's also dependent on the nucleophile itself. So we can express that in terms of an equation that says the rate equals some K, which is an equilibrium, some constant. It's not the equilibrium constant, it's a constant, times the concentration of the alkyl halide or whatever substrate with the leaving group you have, times the concentration of the nucleophile. Now in this type of reaction, if you remember kinetics from general chemistry, we say that the reaction is first order with respect to the RLG because the superscript is 1, right? So if the superscript was 2, it would be second order for that particular reactant, right? We also say that the reaction is first order with respect to the nucleophile because again there's a 1 as a superscript. And overall the reaction is second order. And this is one of the reasons why we call this a bimolecular reaction. Remember, SN2 stands for nucleophilic substitution bimolecular because two molecules are involved in the rate determining step. So that's important to understand that both the alkyl halide and the nucleophile are involved in the rate determining step. Now let's explore some characteristics of an SN2 substitution reaction. And the first thing that we're going to take a look at is stereochemistry. So when we think about a substitution reaction taking place, there are 3 possible stereochemical outcomes of that substitution. So let's explore the possibilities and then actually see what happens in an SN2 reaction. Well, the first possibility is that I can take my nucleophile, and if I react it with a stereogenic carbon that contains the leaving group, right? So this carbon has 3 different substituents on it, and therefore it's a stereogenic center, right? And a reaction takes place in which the nucleophile basically replaces the leaving group. So somehow the nucleophile is coming in the kind of the same direction as the leaving group, and the leaving group comes off, right? And so you have the leaving group is coming off as the anion, and of course the groups coming off of that stereogenic carbon, they don't change in their location. This is what we call a retention of configuration, where the configuration of the stereogenic carbon is retained. Nothing changed other than the nucleophile replacing the leaving group, right? So that is one possibility. Another possibility is where you have the nucleophile coming in from the opposite direction of the leaving group, and so notice what's happening to that stereogenic carbon. The groups 1, 2, and 3 basically move away from the nucleophile, so as the nucleophile is approaching from the opposite side of the leaving group, then that stereogenic carbon has to somehow change its geometry a little bit. But notice the orientation of the substrates 1, 2, and 3. 1 is in the plane of the board. It's still in the plane of the board. It's just going from left to right. 2 is still behind the plane of the board, but now it's oriented from the left-hand side to the right-hand side, and likewise with 3, right? And then, of course, we get our leaving group coming off. So what has happened to that stereogenic carbon? It has inverted, and we call this an inversion of configuration. Inversion of configuration. The last possibility is where the nucleophile reacts in some manner to the stereogenic carbon with the leaving group, and in essence you get both possibilities. You get both retention of configuration and you get inversion of configuration. And then, of course, the leaving group comes off. In this particular case, this is called a racemization. Now, it doesn't necessarily mean you have a racemic mixture. We have to be careful in terms of our language here. If there was another stereogenic center somewhere on the molecule, and nothing happens to it, so its absolute configuration remains the same, then the end result is you get 2 diastereomers. That's not a racemic mixture. We're assuming here that you have in our molecule only one stereogenic carbon, and it happens that that stereogenic carbon has the leaving group. In that case, then you would certainly get 2 products that would be enantiomers of one another, and you would get a racemic mixture. Hence the term racemization. So racemization is kind of a generalized term. Okay. So when we look at what happens when an alkyl halide undergoes an SN2 substitution, we see that most primary and secondary alkyl halides undergo inversion of configuration. Now you might be saying, well, how do you know this? Well, let's think about how we would know what's going on at a stereogenic carbon. What do? We study the optical rotation of that particular reaction. And there are various ways that we can do this. One potential way is to take a nucleophile, let's say iodide, and we can actually use radioactive iodide, and we can monitor a chiral molecule that has iodine as a leaving group. So for simplicity's sake, let's say that our radioactive iodide reacts with this alkyl iodide, and let's say the alkyl iodide has an R absolute configuration. When the radioactive iodide reacts, notice our product is going to be the same as our starting material. It's just that we get either inversion of configuration where the absolute configuration changes, or we get retention of configuration where the absolute configuration remains the same and the optical rotation remains the same, or we get a racemization where you get both R and S, and eventually the optical rotation would go to 0 because you have a racemic mixture. And so when we do this, we actually see that we get inversion of configuration, where the absolute configuration is changing to to S. Why do we know that? Because as we follow this reaction, what happens is the optical rotation initially goes to 0 because you're starting to form the S and the enantiomer. As more product forms, eventually the optical rotation reverses signs, and therefore we know that inversion is occurring in this process. Now, obviously, if you look at this, the leaving group and the nucleophile are the same species. You might be saying to yourself, well, can't the reverse happen? Can't iodide, normal iodide, then react with the radio-labeled alkyl iodide? And that's certainly a possibility. And the way that we get around that is we use a huge excess of radioactive iodide, so that when iodide comes off, there's just very little of it present in solution, so we can actually see what's going on in that process. Okay, so we know that in an SN2 reaction, we get inversion of configuration. What does this mean in terms of the overall mechanism? Well, it must mean that the nucleophile has to approach the substrate from the rear of the departing atom, the halide or whatever the nucleophile is. And we refer to this as backside attack or backside displacement, right? The nucleophile is coming in from the backside of where the nucleophile is relative to that carbon. And so we can start to get a little better picture of what's happening in an SN2 reaction where we have some nucleophile, and notice I always have a negative charge, but nucleophiles don't have to be anions, although many of them are. And so now that nucleophile is going to attack the carbon from the opposite direction of where the leaving group is, notice. And now I get an inversion of configuration and my leaving group comes off. So I've formed a new carbon nucleophile bond, right, whatever that nucleophile is. And then the electrons from the carbon leaving group are going to the leaving group, and we get an anion out of that. So now we have uh, um, a little bit better picture about what the mechanism is. Now we should always ask ourselves, why do we only see inversion of configuration? Why, therefore, is backside displacement the only thing observed? And where do we go to look for an understanding of this? That's right, MO theory. So if we think about what we've learned so far in terms of molecular orbital theory and how the HOMO of some orbitals interact with the LUMO of others, you know that there has to be some type of orbital interaction between the nucleophile and that the orbital of the carbon with the leaving group, whatever that leaving group, let's say that halogen, right? So we have a carbon halogen bond, the halogen's coming off, the nucleophile has to interact with that particular orbital. Well, what orbital is it going to react with, right? So we know it has to interact with an orbital, but there are two orbitals between two atoms. You have a bonding orbital and an antibonding orbital. And most of the time we've seen that the LUMO is an antibonding orbital because it's empty. And certainly in this case, we can envision a nucleophile, right? So here's my nucleophile. It has a non-bonding pair of electrons, so it's in some orbital with non-bonding pair of electrons, and it's going to interact, and it could interact with, this would be the bonding orbital between the carbon and the halogen, or whatever that leaving group is, right? Now, notice, this is going to be a very weak interaction. Why? Well, number one, because most of the electron density resides in between the carbon and whatever that leaving group is. Right? And so you have very small lobes on the opposite, on the other side basically of the carbon. And so that's going to be a very weak interaction. But more importantly, that orbital is already filled with 2 electrons, and so it can't accept any more electrons. And therefore, of course, we have to look at the nucleophile interacting with the antibonding orbital. So this is what the antibonding orbital between a carbon and a halogen or whatever leaving group would look like, right? You would have a nodal plane between the carbon and the halogen, and the lobes would be larger in the opposite direction. So the lobe of the carbon would be larger on the left-hand side than it would be closest to the leaving group. Now you see that for the antibonding orbital to interact with the orbital of the nucleophile, you have excellent possible overlap. And that's exactly what happens, right? So the nucleophile is interacting with the antibonding orbital, sigma star, of that carbon leaving group, just like we've seen many times before. Okay? So, why do we never observe a front side displacement, right? In other words, why don't we see retention of configuration? If retention of configuration occurred, then the nucleophile would actually have to displace the leaving group from the front side, and there would have to be a front side attack. Well, again, we've already seen that the nucleophile can't really approach the bonding orbital because it's full, so we can again explore what that antibonding orbital would look like and how the nucleophile would approach. Well, the only way that it could approach the carbon was in this direction, right? So it would have to approach that carbon because the leaving group is still present there, basically perpendicular to the carbon, the bond between the carbon and the leaving group, whatever that is. And so now you see in that um, orbital overlap, the possible orbital overlap, we see we could create some type of bonding, although it would be weak, but then we would also have an antibonding. And if you remember from the very first time that we talked about molecular orbital theory and the geometry of how orbitals overlap one another, you would remember that when you have a scenario like this, it is called orthogonal bonding, which doesn't exist, right? You can't create a bond um, when two orbitals approach one another and they are orthogonal to one another. And that's why we never see front side displacement. So it becomes explainable, right? SN2 substitution is explainable using MO theory, that the only orbital that a nucleophile can interact with is a sigma star orbital between the carbon and the leaving group, and that you can't approach it from the front side because of orthogonal bonding. So now we have an even better picture of an SN2 mechanism, right? And let's simply recap what we've already talked about. We see that the rate of the reaction depends on both the substrate, the alkyl halide, or whatever leaving group is on there, and the nucleophile, right? Which means that they are both involved in the rate determining step. Right? That's important to understand. They're both involved in the rate determining step, and therefore the transition state has to involve both of them. We're going to explore that in just a little bit. But secondly, we now understand the MO behind it, that the non-bonding HOMO of the nucleophile has to approach the sigma star LUMO of that carbon halide bond, or whatever leaving group we have. Okay, so those are two parts, two pieces of the puzzle of understanding the SN2 mechanism. And there are other factors. We're going to explore those other factors, but at least we can now start to kind of visualize this picture about what's going on, where we have the nucleophile and its non-bonding pair of electrons, the HOMO non-bonding pair of electrons. It's going to interact with the LUMO sigma star of that carbon leaving group bond because it's empty, right? I mean, that's an important feature. It's empty and it has good overlap. And so at some point, we're going to develop a transition that looks like this. So this would be the transition state where now as a nucleophile comes in, it starts to overlap with that sigma star orbital. And at the same time, the carbon halide bond is going to be breaking. And so you have a transition state that looks something like this, where the carbon is what we call pentacoordinate, because there are 5 bonds attached to that carbon. Now recognize this is a transition state, and in this transition state, carbon has to be sp2 hybridized, or at least near sp2 hybridized, but we can never isolate a transition state. So do we ever see carbon that's this would be trigonal bipyramidal? We never see that. but we can envision that at some time that there's a snapshot of that carbon in which it has to be bonded or partially bonded to both the nucleophile and the leaving group. And therefore we can um, draw a potential energy diagram of this particular reaction where we start at some arbitrary energy where we have the nucleophile and the alkyl halide, and that alkyl and the nucleophile then starts to approach the backside of the leaving group, and of course there's going to be some initial repulsion there because of the electron-electron interactions, but eventually you're going to get to inversion of configuration to form our new product. So what's happening in that process? It's a one-step mechanism in which we have to add some type of energy, right, activation energy, to produce that transition state where the nucleophile has approached enough to start to form a bond with the carbon, and now that carbon bond to the leaving group is weakening because we're adding electrons into its antibonding orbital, right? So now you get a really kind of a cool picture about what's going on. The nucleophile starts to add electrons and form a bond to the antibonding orbital of that carbon leaving group, and as it does so, it breaks the carbon bond between it and the leaving group. So that would be the transition state. We call this a pentacoordinate transition state. And the energy barrier is that activation energy in which you have to supply it to get to that particular state, right? So now we have a cool little picture of an SN2 mechanism. Nucleophile approaching, leaving group coming off at the same time. Now notice both the nucleophile and the alkyl halide are involved in that transition state, right? Which explains the kinetics of the reaction. Both of them are required to be present in order to form product. And that's a very important concept to understand, right? This is why the reaction is bimolecular, because both molecules, the nucleophile and the alkyl halide, have to be present in order for product formation to occur, in order for the rate determining step to even proceed. Okay, so now we're going to explore some of the aspects of the reaction. And one of the first things that we're going to take a look at is the effect of the substrate, the R group. How does the R group affect the rate of the reaction? And so what we're going to do is we're going to compare the R group to a relative rate. Now, what do I mean by relative rate? Well, we're going to relate R groups to the methyl group. So I'm going to use the methyl group as a standard, and its relative rate is going to be 1. That's my standard. Now, how do other groups compare? So if I think about what is attached to that carbon, I have a halide, right? So I have some halide or some leaving group, and now I also have 3 hydrogens attached to it. So now, what if instead of I replace one of the hydrogens with a methyl group? What happens to the relative rate? Well, it goes down to 0.033, right? And so we see that a methyl halide is faster than an ethyl halide in terms of substitution. Okay, so I can extend that, instead of having a methyl group, I could have an ethyl group on the carbon. So understand what we're doing here. The carbon on the right is attached to my leaving group. It has 2 hydrogens and an ethyl group attached to it. Right? So that's the carbon that's being attacked. It's the carbon on my right that's being attacked. Always the carbon on the right that is attached to the leaving group. So what have I done? I've gone from having 3 hydrogens to now 2 hydrogens and a methyl group to 2 hydrogens and an ethyl group. And I see that, again, the rate goes down a little bit. Why? Well, the only difference is an ethyl group is a little bit bulkier, a little bigger than a methyl group. And a methyl group is bigger than a hydrogen by far. So what can we do next? Well, we notice that these are primary alkyl halides. What if we went to a secondary alkyl halide where there were two methyl groups attached to the carbon with my leaving group? So now my carbon has only one hydrogen, it has two methyl groups, and then of course it has a leaving group. What happens to the rate when I take some nucleophile and I react it? Well, it goes way down to 8.3 times 10 to the minus fourth. So what have I done? Well, I've now added another methyl group to the carbon with my leaving group. And it becomes kind of apparent that the more R groups are on that carbon, the harder it is for the nucleophile to reach that carbon and displace my halide. I can see that even, right? So I have a secondary alkyl halide. Notice primary alkyl halides react. Secondary alkyl halides much slower. What if I had a primary alkyl halide, but it had an isopropyl group coming off of it, so a much bulkier group? Well, notice it's even slower, right? So why? Well, because that's a primary alkyl halide, but it is a bulky primary alkyl halide. So again, that bulk plays a big role in it. And it's so much so that if I had a tertiary alkyl halide, the relative rate of this reaction is 0. In essence, tertiary alkyl halides do not react by an SN2 substitution mechanism. Interestingly enough, if I take an allele substituent, remember this is an allele substituent, so I have a double bond CH2 CH and then a CH2. That CH2 on the right is called an allele carbon. And if I look at, so this is not just a primary alkyl halide, this would be an allele halide. And its relative rate is 1.3. Why is that? It all has to do with resonance, where I can basically move electrons around and I can stabilize any charges that are brought on. I can stabilize those charges by that pair of electrons on the carbon. So the take-home message is that steric effects play a role. They slow the approach of the nucleophile, and therefore if you have a bulky substituent coming off of that carbon that has a leaving group, you're going to slow the rate down considerably. And even so much so that when I have tert-butyl halide, or a tert-butyl group with a leaving group, those methyl groups are surrounding that carbon such that the nucleophile can't get to that carbon at all, and therefore the reaction doesn't take place, right? So we see that the substrate plays a crucial role in that SN2 mechanism. Methyl halides undergo SN2 mechanisms very readily. Primary alkyl halides, not so readily, right? But they still happen. So methyls are very fast. Primary alkyl halides, they happen. They're much slower than a methyl halide, but they can certainly happen. As you add bulk to a primary alkyl halide, you decrease the rate, but you can still get an SN2 substitution. Secondary alkyl halides, the rate slows down even more so, but you still can get an SN2 substitution to occur. It's when you get to the tertiary alkyl halides that no substitution is ever going to occur via this SN2 mechanism. Now we do know that tertiary alkyl halides do undergo substitution, and therefore there has to be another mechanism that we will explore in just a little bit. But they do not undergo SN2 substitution. Okay, now when we look at cyclohexyl alkyl halides, there's an interesting phenomenon comparing secondary cyclohexyl bromide with a typical secondary alkyl halide. And that is that secondary cyclohexyl bromide reacts much slower than your typical alkyl halide. And if we take a look at, understanding why that occurs, here we have our chair conformation of the cyclohexyl bromide. The bromine is in the equatorial position because this is going to be the most favored conformation of this particular molecule. And if we think about the sigma star antibonding orbital that is going to interact with our nucleophile, let's say that nucleophile was iodide. So iodide approaches, and you see that there really is no steric effects that are apparent. So steric hindrance doesn't appear to be a factor. It isn't until you start looking at what else is attached to that ring. And we know that there are two hydrogens that are axial hydrogens. And those axial hydrogens are basically going to block the nucleophile from approaching. And therefore, we do get a steric effect, but it doesn't have to do with what's attached directly to the carbon. It has to do with those pesky axial hydrogens. And so this is why we can explain phenomenon like that, which is kind of cool. When we see odd things happening, we should be able to explain them, looking at the geometry of any particular molecule. And so that shows you how the substrate can play a role in SN2 substitution. But the substrate isn't the only thing that that's involved in the rate, right? We have the substrate, we also have the nucleophile. And so the next thing that we can take a look at is the effect of the nucleophile. And we see that the best nucleophiles are the ones that overlap with that sigma star carbon leaving group bond the best. Now, how do we predict that? Well, predicting this becomes pretty difficult to do. And so, you sometimes have to kind of get a feel for what's going on. And there are certain trends, and we're going to take a look at those trends. And if you look at table 7.5 in your textbook, they have a really nice table that shows you some relative nucleophilicities of common species. So nucleophilicity is how good of a nucleophile something is. And we see that there are some excellent nucleophiles. So cyanide and mercaptide and iodide are very good nucleophiles. Then there are some good nucleophiles: hydroxide, bromide, azide, and 3, ammonia, nitrite. And then there are some nucleophiles that are okay. So chloride and fluoride fall into this category. Fluoride isn't a very good nucleophile. And you also have some neutral nucleophiles. Alcohols and water can be nucleophiles, but they're not great nucleophiles, right? So you notice that most of these nucleophiles have a negative charge. They're anions. Ammonia is really the only one that stands out that isn't an anion. But in general, we can look at some trends, and we see that typically speaking, anions are better than neutral species when it comes to nucleophilicity. So we see that hydroxide is better than water, right? So here's hydroxide and here's water. But there are other trends that follow that really aren't on this table. For example, methoxide is better than methanol. Ethoxide is better than ethanol. So in general, alkoxides are better nucleophiles than alcohols. Amide is a better nucleophile than ammonia. So ammonia is it's a good nucleophile, but the amide anion is a better nucleophile. And in general, this trend follows the basicity of the species. Hydroxide's a better base, methoxide's a better base than methanol, amide is a better base than ammonia. We also see, going across the periodic table, that amide is a better nucleophile than an alkoxide, which is a better nucleophile than a hydroxide. And of course, this also follows basicity. So can we say that nucleophilicity follows basicity? We've already defined a nucleophile as a Lewis base, right? Those terms are interchangeable. But the trends don't always follow, they don't always parallel one another. For example, we see that H2SE, hydrogen selenide, is a better nucleophile than hydrogen sulfide, which is a better nucleophile than water. This goes against basicity. We see that phosphines are better nucleophiles than amines. We see that the halides, iodide is a better nucleophile than bromide, which is a better nucleophile than chloride, which is a better nucleophile than fluoride. And so these are all opposite that of their basicity. They do not follow the trend in basicity. And in general, what you're seeing there is when you go down the periodic table, it appears like the trend is reversed. The reason for this is because atoms higher up on the periodic table have stronger interactions with the solvent, and therefore we say their nucleophilicity is decreased. Now we can see that in this table right here, right? So what's happening here? Well, we run a reaction, a substitution reaction of a halide with methyl iodide in water, and we study the rates of the reaction of the halide that we're using. And we see that iodide's a great nucleophile, right? It has a relative rate of 160 compared to chloride, which has a relative rate of 1, and fluoride isn't even on the scale. So it's important to understand the solvent effect. Well, water is a good, very polar protic solvent, right? So fluoride and chloride are bases. They're strong bases relative to bromide and iodide. And in polar protic solvents, what happens is they act as a base to the solvent. They interact with the solvent and are surrounded by the solvent. What happens is the effect is that this decreases their ability to interact with the substrate. They're too busy interacting with the solvent to actually interact with the substrate. And so we say their nucleophilicity is suppressed. Now, we can see that because when we take and we change the solvent to acetone in that second reaction, where you have a polar solvent but it's not protic, then what happens? Basically, the reverse trend occurs, where now chloride is the better nucleophile. Again, fluoride isn't registered. Fluoride is kind of a tricky one to use, but you see a general trend that is reversed, that now iodide is the weaker nucleophile, followed by bromide, followed by chloride. And ultimately, when you have no solvent in the gas phase, then you see iodide is a very poor nucleophile, and fluoride is the best. So the trend is reversed. And this plays a role. So we see that solvents and nucleophiles play a role. We see the effect of nucleophile, but we also see the solvent playing a role in this aspect as well. So it's important that our solvents are selected in a way that doesn't suppress nucleophilicity. And therefore, generally speaking, for an SN2 reaction, we want a very polar solvent, but we tend to try to shy away from protic solvents, unless, of course, our nucleophile is a very strong nucleophile, then it really doesn't matter. But in general, for SN2, we want a polar aprotic solvent like acetone, THF, acetonitrile. These types of solvents, DMSO, DMF, right? If we refer back to our table of polar aprotic solvents, these are solvents that we like to use for SN2. Now, what about the leaving group? In general, the more stable the leaving group is, the easier it is to displace. Why? Well, because remember, the leaving group's coming off as an anion. And therefore, the more stable that anion is, then the easier it is to come off because it's not going to react. Stability and reactivity um, are typically inverse of one another, right? The more stable something is, the less likely it is to react with something. And in general, this follows the trend of the pKa of the conjugate acids, right? So, for example, we saw that iodide is a good leaving. We see that iodide is a good leaving group. Why? Well, its conjugate acid has a very low pKa. So the lower the pKa of the acid, the more stable its base. The more acidic an acid is, the more stable is its conjugate base. And we see that trend that iodide's a good leaving group, bromide's a good leaving group, chloride is a good leaving group. This is why we use alkyl halides as functional groups in nucleophilic substitution reactions because the halides come off very easily. But notice we have other leaving groups. So for example, the sulfonate is a good leaving group. Water is a good leaving group. But some of the poorer leaving groups, fluoride isn't a very good leaving group, so we typically don't use alkyl fluorides for reaction with nucleophiles. Also notice alkoxides are bad leaving groups. OHs, so alcohols, right, ROH, alcohols don't undergo substitution reactions very easily. And this is important to understand, and we're going to explore how we can make better leaving groups in the next video.